Electromagnetic waves comprise what's known as the electromagnetic spectrum. Now, spectrum comes from, I believe, the Latin for specter or ghost, because when you, and most of you have probably seen this, when you shine light through a prism, or if sunlight reflects off of water droplets in a certain way, you get a rainbow effect. That rainbow is called a spectrum. Now, that rainbow only is a small part of the full electromagnetic spectrum. There are 7 types of electromagnetic radiation or electromagnetic light. Now, radiation here means light. We have radio waves, microwaves, infrared radiation, visible light, ultraviolet radiation, X-rays, and gamma rays. Those are the 7 types. These are all the same phenomenon. They are all electromagnetic waves. The only thing that separates these 7 things is the wavelength. Now, your eyes are only sensitive to a very small range of electromagnetic radiation. We call that the visible. Infrared was detected in the year, I believe, 1800 by William Herschel. Ultraviolet, infrared means beyond red, ultraviolet means blue, more than violet. And the others were discovered in various instances. Röntgen discovered X-rays by accident. These 7 types of radiation have different applications, and your book goes through some where you can use some of these different radiations. Of course, radio waves, popular in communication. Our cell phones use radio communication, cell towers, radio towers, and so on. Microwaves, everyone knows the usefulness of a microwave oven, but microwave ovens only use a very specific frequency of microwave light. There are actually other ranges of microwave radiation that don't heat up your food, but can be used for communication and so on. Infrared. Infrared light, night vision, or thermal glasses, thermal goggles. If you have a thermometer that you stick in your ear and take a picture basically, or swipe your forehead, as they do in modern hospitals, those are infrared sensitive thermometers that measure your body temperature by the light that you give off. Right now you are literally giving off light in the infrared. We can't see it with our eyes, but you can detect it with instruments. Visible light, obvious, useful visible light, right? Traffic signals, we can see when it's safe to go or not. We can read books, we can watch television, all those fun things using infrared light. Ultraviolet light, beyond burning your skin and having to use sunblock from the sun's ultraviolet light has medical applications. A lot of LASIK surgery uses ultraviolet lasers to cut into the cornea. X-rays, obvious medical applications for X-rays, detection of broken bones, dental X-rays, and so on. And gamma rays, again, medical application, gamma knife surgery to remove brain tumors, that sort of thing. So they're all the same phenomenon. And I only mentioned a small sampling of what you could do with these various types of radiation. Now, there are 3 general rules for electromagnetic waves. They don't fit in every instance, but the general rules are high frequency waves, and these are arranged from low frequency to high frequency. So radio waves are the lowest frequency type of light. Gamma rays are the highest frequency, highest energy form of light. High frequency waves penetrate materials better than low frequency light. That's why we use X-rays for medical purposes, because the X-rays can penetrate our skin more easily than visible light can. We have high frequency waves can carry more information than low frequency waves. This is incredibly important when talking about cellular networks. Modern cellular networks try to use higher frequency ranges because more data can be more quickly communicated. And additionally, AM versus FM on your radio. If you ever wondered why FM sounds better than AM, is because FM is typically around 1,000 times higher frequency than AM radio stations, so more information can be transmitted. A clearer sound, stereo sound, and additionally hidden basically in modern radios, track information. So that's how your stereo knows, for modern stereos, what track is currently being played, or what radio station is currently on. And then the smaller the wavelength of radiation used to probe a material, the more detail you can resolve. So for like microscopes and things like that, the the higher frequency, smaller wavelength light you use to probe an object, the more detail you can pull out of that object. Now, again, these are general rules. Electromagnetic radiation transports through a vacuum without a problem, but once it tries to go through materials, different radiation has different issues going through materials. We just said how high frequency radiation can penetrate materials better, but there's some materials that are just transparent to some forms of radiation and not transparent to others. An obvious example of this is a window. Glass is visibly transparent, right? That's why we use it. We can see through it. Visible electromagnetic radiation can easily penetrate glass, but infrared radiation cannot. So when sunlight on a hot summer day goes through your car's windows and strikes the seat, it strikes the dashboard, that energy is absorbed by the material and it is re-radiated as infrared light. That infrared light can't go back through the window. It's trapped. The window looks black to it. So that infrared radiation is trapped in your car, causing your car to heat up, right? That's how a greenhouse basically works. Visible light comes in, infrared radiation can't escape. There are some materials that are transparent to some wavelengths and not others. For example, quartz. Quartz as a rock is not visibly transparent, but ultraviolet light can get through quartz like it's glass, right? Mostly transparent in the ultraviolet. So you can have different phenomenon, different EM radiation behave differently in materials. Some materials reflect various radiations, some absorb them, some transmit them. Your book continues in pretty detailed information. Each of the 7 ranges of electromagnetic radiation we talked about, from radio to gamma rays, and talks a bit about the application in each range. I just want to focus in on a few of those, but please do read through that information. So radio waves, for instance, one thing it does touch on is amplitude modulation versus frequency modulation. Now, you've probably all experienced at least one of these if you've ever played with a car radio, right? You have AM channels and you have FM channels. And what's the difference? Why do AM channels sound sort of monotone? Why isn't the signal as rich? FM stations sound a lot cleaner, but they don't travel as far. You can't hear the stations from as far away. What's the difference? Well, AM modulation means amplitude modulation. Now, in all radio stations, AM or FM, you start with what's called a carrier wave. That's the wave that you tune your radio station in on. So, 1070 AM, blah, blah, blah. That's 1070 kilohertz. That is the carrier wave. And what the radio station then does is it slightly modifies the carrier wave by adding or subtracting the amplitude of the wave, so making the wave stronger or weaker. Another way of thinking about it is if this was a light source that you could see with your eyes, imagine we're the car and we can actually see this radiation, it's basically the source getting brighter and fainter. So it would be like me communicating with a flashlight at some distance by turning up and down the brightness. That's amplitude modulation, as opposed to frequency modulation. Frequency modulation, again, starts with a carrier wave, 90.9 FM in Wausau, NPR, Wisconsin Public Radio. That is 90.9 megahertz, or millions of hertz. So you start with that band, that carrier band, and rather than changing the amplitude slightly, they change the frequency slightly. So it's a little bit less than 90.9 or a little bit more than 90.9. And they vary the frequency of the wave. So again, if you could see this light, effectively what they're doing is changing the color a little bit. So they start off with orange light and they make it a little bit redder or a little bit more yellow. And your car then sees that difference in the frequency and can interpret a signal from that. So the two have different advantages and disadvantages. AM radio stations came first, FM came later. Because FM is a higher frequency, you're talking about megahertz in frequency rather than kilohertz, more information can be packed in an FM radio signal, which is why you can have stereo music rather than single channel monochrome music or monotone music. You can have more detailed, more clear radio stations, and you also know there's less popping, cracking, and hissing in an FM signal versus an AM signal. And the understanding behind that, again, it's useful to use the light analogy. For AM channels, you're turning up and down the brightness of a light source to get a signal across. But other things can change the brightness of a light source. If you've ever driven, and the sun is on the horizon, and you've driven past a tree with a bunch of leaves in it, you see the sun get brighter and fainter as it moves behind the tree with leaves. So in an AM situation, other things can reduce the signal strength. It's not just the radio station itself, but if you go under a bridge or past a building, the signal can weaken, which means that the signal can get noisy. For an FM radio station, it's the color that's changing. So it doesn't matter if the signal gets a little bit weaker or a little bit stronger, it's the same color. So my analogy is, now instead of the sun passing a tree with leaves, imagine the sun was changing color slightly. Well, the color isn't affected by passing behind a tree. Sure, it gets fainter, but the sun would still, if it's red, it would still look red. If it's blue, it would still look blue. So the color isn't affected by this brightening or fainting of the signal. So you get a clearer signal with FM, and you have more information. Unfortunately, FM radio signals also cost more money to broadcast because you need to put more power into the signal generator because you're changing the frequency quite a bit more rapidly. It requires more energy to send out these signals, and they don't go as far. So that's between amplitude and frequency modulation, AM and FM on your radio dial. And radio has a bunch of, they talk about extremely low frequency radio signals that submarines use that can travel through basically the Earth, but carry very little information. It takes a long time to get a signal, a message across using this very low frequency signal. They talk about television. Most television nowadays must be on cable TV or satellite, but if you don't, you have VHF and UHF, very high frequency or ultra high frequency radio signals. So the radio band itself isn't just the radio that your car receives. The radio band actually has a huge number of discrete areas broken up where they're dedicated to various signals. So if you ever looked at the FM dial in your car stereo, it's limited, right? It doesn't go much below, I think, 87 megahertz. It doesn't go much above 108 megahertz. So what's above that, what's below that? Well, there are different areas set aside for those radio signals. CB radio operates 40 channels, operates at a very specific range. The emergency services have their own radio bands. Military have set aside radio bands. Communication with airplanes, right? When the pilots get their information from airports, that's on a very specific radio band that no one else is supposed to use. So airplanes don't get interfered with. The cell phones, the cell phone networks, the LTE networks, the 4G networks, your Wi-Fi routers, the cordless telephone you might have in your house, all of those have a set range at which they can operate, set aside by the US government. The airwaves all around us are owned by the taxpayers, you and I. We set aside some areas for use, other areas we sell, like for example the cell networks, Verizon, AT&T, Google, all have bought part of the spectrum that they are allowed to use to send out their cell signals, and no one else is supposed to use that part of the cell network. So that's radio signals. If you want to see what the different radio bands are broken into, there are many websites you can go to that detail what radio frequencies are used for what. I'm going to skip over the others and jump to visible light. Visible light, the light that you and I see from, most of us, unless you're vision impaired or colorblind, you see the full range of colors. Typically the rainbow colors are broken up. The mnemonic to remember it is Roy G. Biv, right? Red, orange, yellow, green, blue, indigo, and violet. Although these last two are kind of, in my opinion, the same thing. The 7 colors represent our interpretation of these different wavelengths. Our eyes interpret the wavelengths of light as different colors. 400 nanometer light is as short of a wavelength that we can see with the human eye. That corresponds to, violet. 750 nanometers is the longest wavelength of light that we can see. That corresponds to red. So orange is somewhere in the high 60s, yellow, in the low 600s, sorry. Yellow in the low 600s, green, 550 or so, 600, 550 nanometers and so on. We interpret these colors, again, if you're not vision impaired or color impaired, you see this full range of colors. But 10% of males are blue-green colorblind, so they have receptor difficulty detecting the difference between blue and green light, and then a smaller percentage of both men and women are completely colorblind. So if you are, I try to, I'm not going to focus in on this anymore than just to mention that the colors represent different wavelengths of light that we see. So visible light, again, incredibly useful for getting information across. And then it moves on to ultraviolet light, X-rays, and gamma rays. It talks about how those different wavelengths are used in industry and in medicine and in our everyday lives. The electromagnetic spectrum, the thing to take away is it's the same thing. They're all electromagnetic waves. The only thing that differs is their wavelength.